everybody, and welcome to the Unit 10 review session. Our Unit 10 is on reaction rates and equilibrium. The format of your test will be 16 multiple choice questions, and you will have 4 free response. The free response will be multi-part, so there'll be an A, B, C, all of that type of information. So this unit was really broken up into 2 parts. We first talked about reaction rates, then we went into equilibrium. So just a couple reminders as far as things to overall review. All right, please make sure that you do review the potential energy graphs and that you feel comfortable with all of the different parts of those graphs, knowing whether a reaction is exothermic or endothermic. All right, being able to look at that graph. Remember, exothermic reactions have a delta H. That is a negative value. Endo is a delta H. That is a positive value. An exothermic graph, I'm not going to draw this to scale or use any values, but an exothermic graph, you have your reactants starting here, going up to your activation energy, and your products will be below your reactants because energy has been given off. So here are your reactants, here are your products. This is an example of an exothermic graph. Whereas an endothermic graph, your reactants start at a lower energy than your products. Okay, energy has been taken in for that reaction. All right, and we can see here that we would have a positive delta H. Also be able to identify things such as where the activated complex is, which is the top, the peaks of those graphs, the activation energy, which is the energy it takes to go from reactant up to the activated complex. All right, and then also make sure that you're comfortable understanding what a catalyst does, which is it brings that activation energy down. Okay, all right. So we're going to go through several different types of problems, and as we go through these, I will talk about different types of questions that can be asked with them. So let us start out, with a reaction rate problem. For the reaction x plus y yields xy, the following data was obtained. And I've given you 3 different trials, 3 different experiments for this reaction. So first thing I'm asking you for is for the rate law. So for rate laws, it's always written the word rate is equal to lowercase k. I use a cursive k. You don't have to. You can just use a regular k. Times the concentration of your reactants. All right, so you have x as one of your reactants, and that's going to be to a certain power. We have to figure out what that power is, times the concentration of y to a certain power. All right, so this is our job. We have to figure out what those exponents are. Those exponents tell us how that reactant impacts the rate. And here's where we go up to our experimental evidence. I first just want to get information about x. Okay? So I'm going to choose 2 trials where y is constant, because I can't have x and y both changing. I have to have one that is going to stay the same, if at all possible. And in this case, I do. I have trials 1 and 3. All right, trials 1 and 3, y is the same. So any changes that occur between 1 and 3 is due to the reactant x. So I'm going to look at my trials. I'm going to first look at my concentrations. I see here that in trial 1 I'm 0.36 and in trial 3 I'm 0.18. All right, so from 0.36 to 0.18, we know that's a half. I don't like to think in terms of halving. I'd rather think in terms of doubling. It's just a little easier for me. So I'm just going to go instead from 1 to 3. I'm going to go from 3 to 1. So I'm going to say, all right, what happens to my concentration? My concentration doubles, all right, because 0.36 divided by 0.18, 0.36 divided by 0.18, okay, that's a 2. That doubles. So let's see what happened to the rate when we went from 3 up to trial 1 right there. So, and if you're not sure, obviously this math is not particularly challenging, but if you have one that's a little bit harder, you just take the bigger number, 0.43, all right, and divide it by the smaller, 0.215. And that also doubles. If you get a situation like this one where you doubled the rate, you doubled the concentration and the rate also doubles, that particular reactant is going to get an exponent of 1, or we call it, it's a first order situation. It's because I doubled and I doubled, it gets the exponent 1. Okay. Now, let's take a look at y. Now we want to figure out what's going on with y. So I need to choose two trials where x is the same, and my two trials where x stays constant is 1 and 2. All right, so from trial 1 to 2, all right, I see that my concentration of y doubled. Okay, and my rate, and again, if I'm not totally sure, I'm going to take the larger number, 1.72, divided by the smaller, 0.43, and I got a 4. So you doubled the concentration, and the rate doubled. I'm sorry, and the rate quadrupled. So if you doubled concentration, and the rate quadruples, that exponent is a 2. Okay. All right, so again, if you double and double, you can kind of think of it as like 2 over 2. That is going to give you an exponent of 1. If you double and the other doubles. If you double the concentration and the rate therefore quadruples, all right, that's going to be an exponent of 2. Your only other scenario with this is if you change the concentration of one of your reactants and the rate does not double, all right, so if you get no change in rate, you're going to get an exponent of 0. So please remember that, all right? So double, double, it's a 1. Double, quadruple, it's a 2. No change, it's going to be a 0. All right, so you did your hard work here. Letter A is answered. The rate law is written just like that. It is first order for X. It is second order for Y. The total order of this reaction would be third order. And all I did there to get those values is to add those exponents. Part B, I am asking for the rate constant. So I want you to solve for K. All right, so I'm going to do the algebra of that first. So if I want to solve for K, it's going to be rate over, I just divided each side by concentration of X, which is to the first, so I don't really write that anymore, times the concentration of Y squared. To get values for this, choose any trial. I just stick with trial 1. It makes no difference, but I'm just going to go ahead with trial 1. My initial concentration of X under here is 0.36. Of Y is 0.60. You don't need to put the zeros in when you're doing this. Don't forget that gets squared. And the rate is 0.430. Okay. I'm going to go ahead, I put those in my calculator. And you end up getting for this one about 3.32. So K is equal to 3.32. We are not requiring you to give a label for K. For those of you moving on in chemistry, you will definitely deal with the labels and do some more work with that. All right, now that you've found K, I can ask for the rate because you have the rate law and you have K, so you can solve for the rate if I give you certain concentrations. So we know, this is my rate law, so we know rate is equal to K. Well, K is 3.32. All right, times the concentration of X, which I told you here is 0.5. And that's to the first power. I'm just going to leave that there. And then the concentration of Y is 0.9, and you have to square that. Okay? When we solve for that, all right, we end up getting rate is equal to 1.34. Label for that, just always look up at the rates that I give you, and that's going to end up being the label. Moles over liters per second. Another way of saying that is molarity per second. You do need to label your rate. All right, remember molarity is just simply moles over liters, and that's what that is as well. You could have written it this way as well. All right, so lots of good things that can come from these rate law problems, lots of different ways of us asking this. Okay. All right, let us move on to question 2. And question 2, now we're switching over a little bit to equilibrium. Okay. Find the KEQ for a reaction 3x plus 2y yields z if the concentrations at equilibrium are as follows. So here's really the key to this problem. I'm telling you that your values are at equilibrium. That makes this actually a pretty easy problem to do. There's not a lot of work to go into it. First thing you're going to do with any of these KEQ problems is you're going to set up the KEQ expression. All right, KEQ is always equal to product on top, so concentration of z Whatever coefficient the substance has, that's what the exponent's going to be. I'm going to put the 1 there just to kind of tell us that we finished that. All right. Now my reactants go on the bottom, products in the numerator, reactants in the denominator. So x to the 3rd power times y squared. Okay. So that is my KQ expression. Again, I have given you values at equilibrium, so we can just go on ahead and carefully make sure you don't kind of mix these numbers up, plug these in. So Z is 1.90, all right, molar, over X is 0.40, all right, cubed. I'm going to just, you don't need to worry about doing the labels in it. You can if you want to, but you don't have to worry. And then Y is 0.75, and I have to remember to square that. All right, you might want to take a second while I'm doing these problems and obviously pause to put them in your calculator. Please make sure that you're putting them into your calculator correctly. It's always a shame when people have all of the work and then they lose those easy points for calculator issues. When you end up doing this problem, you get a KEQ that equals 52.8. So let's take a second and talk about what KEQ means. First off, KEQ will never, it does not have a label. It is a value that's telling you what's happening at equilibrium. So when you get a value that's very high, like 52.8, that means that you have a numerator that's much higher than your denominator. We know that a value that's over 1, all right, the numerator has to be higher. Well, what does that mean for us? That means at equilibrium, our numerator came from our product. We have a lot of product at equilibrium, all right? That's what our KEQ value tells us. If we were to get a KEQ that was less than 1, that means that we have more reactant at equilibrium. Okay? Just a little note about equilibrium. Please remember it means when we say we have a substance at equilibrium, or I'm sorry, a reaction at equilibrium, it means that both the forward and the reverse reactions are going at the same rate. It does not necessarily mean, and typically it does not mean that you have the same amount of reactants and products. So please make sure that we are clear on that. All right, let's take a look at problem number 3. So for problem number 3, it is another equilibrium problem. Okay. I've given you a balanced equation. The initial concentration of X and Y are 2.5 molar, and KEQ is 2.9. What are the equilibrium concentrations for all species? Now this one is going to take a little bit more, but the first thing that we're going to do, and I'm just going to do it over here to save, make sure we can see it, but save on space, write my expression. Always write the expression first. So KEQ is going to be my product. So Z, oh, that was a terrible bracket. Let me redo that. All right, those brackets, remember, always meaning concentration and molarity. So it's going to be Z squared over the concentration of X times the concentration of Y. They both have exponents of 1 because they have 1 coefficients in the balanced equation. All right, the key to this problem is this word initial. I have given you initial concentrations. Well, KEQ is all about what's going on at equilibrium. You cannot use initial concentrations in a KEQ value. So when I give you initial concentrations, you have to set up an ice table. It is an ice problem. And what do I mean by that? So I have I, C, E, spelling out ice. Along the top, you're going to write out all of the different parts of your reaction. So the concentrations of all of those. All right. Initially, and that is what the I stands for, initially, I'm telling you that your concentration of X and Y are 2.5. So 2.5, you're going to go ahead and write that. They're each 2.5. Initially, your concentration of Z is 0 because initial means before the reaction has happened. So we don't have any Z yet. The C in my ice chart stands for change. All right, well, these reactants are going to start to react, and you're going to lose a certain amount of reactant in order to form your product. We don't know how much, so we're going to call that X. And sorry that that's an X too, but it's a little X like algebra X here. So this is going to be minus X. Okay. Well, whatever this reactant loses, because the coefficients are the same, whatever this reactant loses, this reactant's going to lose the exact same amount. Again, because the coefficients are the same. Your products are going to gain that amount. All right, so it's going to gain, but it's not going to gain just x. There's a coefficient of 2 there. So for every 1 that this loses, this gains 2. So this is going to be plus 2x. At equilibrium, which is what your E stands for, you're going to combine those two. So 2.5 minus x, 2.5 minus x, and this is 2x, okay, because 0 plus 2x. All right, I'm now going to put these back into my KEQ expression that's up here. I've given you the value of KEQ, it's 2.9. So 2.9 is going to equal, all right, now whatever z is, so that's 2x, but I have to square it. So I'm squaring it because that's what I did in my KEQ expression. All right, don't think just because it's a 2 here that takes care of the 2. You do need them in both places if you're thinking of it that way. Then my x times my y. Well, both of them are 2.5 minus x, so 2.5 minus x, and that's going to be squared. Now, we are going to make the math of this pretty straightforward for you. All right, you should never have to use the quadratic equations for the problems that we're going to give you. This is a situation where you can square root both sides, and when you do that, you get the square root of 2.9 to be 1.7, and that's going to equal 2x over 2.5 minus x. That makes the math much easier. I am going to go on ahead, and I'll write this out for everybody just in case you need it. I'm going to multiply each side by 2.5 minus x. All right, so 2.5 minus x over here. That way they divide out. I'm going to distribute this 1.7. So I'm just going to rewrite this down here. 1.7 times 2.5 minus x is equal to 2x. I'm going to distribute this. So 1.7 times 2.5, and that gives you 4.25, 1.7 times 2.5, minus 1.7x is equal to 2x. I want to get my x's on the same side, so I'm going to add 1.7x to each side. All right, so I have 4.25 is equal to, that's 2x, and 1.7x is 3.7x. All right, and then you are going to divide each side by 3.7. And so divided by 3.7, and that gives you about 1.15, so x is equal to 1.15. All right, well, we did a lot of work, all right? There's been a lot of work done on this problem, but we have not answered this question at all. The question was, what are the equilibrium concentrations for all species? So we have to go back to this equilibrium line. My concentration of x is of compound x, all right, is 2.5 minus little x. So what I do is I write concentration of x. It's the same as the concentration of y here. They're going to be the same value. And 2.5, right, so 2.5 minus 1.15, and you get an answer of 1.35 for that in molarity. And then Z, concentration of Z, is 2x, so 1.15 times 2, and that's going to be about 2.3 molarity. And there is your final answer. So you want to really make sure you've done a whole lot of work here. You want to make sure that your teacher can really see what your answer is. And yes, you have to show your work, and you absolutely need to use an ICE chart to complete this in order to get credit. All right. Let's go on ahead to number 4. All right, so number 4 is bringing us back to reaction rates. All right, here we're talking about a reaction mechanism. And remember, a reaction mechanism shows all the different steps that took place in a reaction. Most reactions don't occur in one step, they occur in multiple steps. There's several things I can ask you for given a reaction mechanism, and I've gone over several of them here. So, write the overall reaction. Well, to do that, I'm going to look up at my two parts, okay, and figure out what appears on both sides of the arrow. Okay? So, I'm first going to look A2, B2. Well, that's actually only on the left side of those arrows, so that I can't cross that out. Then I get to X. X is on the left and the right of that arrow. So right now I'm just going to box that, and then we'll talk about it. Okay? All right, what else? Then I'm going to say A2B. Nope, that's only on the right side, so that's going to stay there. XB, there and there. All right, so that's on both sides. So I'm actually going to answer questions B and C, and then we'll go back and do A. It doesn't matter which order you want to do this in. Okay, so for this, I've asked for the overall reaction. So what I'm going to do is write anything that I have not crossed out. All right, I'm sorry. I said I'd do B and C first. So let's talk about catalysts and intermediates. A catalyst is a substance that is used to speed up a reaction. You will first see it, all right, and these are written in certain steps. So there's step 1 and there's step 2. You will first see it on the reactant side, and then you will finally see it on the product side, because catalysts don't get used up. They are reusable. That's why they're so interesting. Okay. So I see here that I have an X on my reactant side and an X on my product side. So my catalyst is actually X. Okay, it's compound X. Now, an intermediate is something that is first produced, and we produced XB, so the first place you'll see it is the product, then it is used up, and so the second place you'll see it is the reactant. It's the opposite of that catalyst as far as how you see it. So my intermediate here is XB. Now, catalysts and intermediates are not written in the overall reaction. So my overall reaction is A2B2 and A2B2, so that's 2A2B2, and is going to yield 2A2B plus B2. Now, what's nice about doing an overall reaction, when you have it there, it should be all balanced, which this one is, and work out well for you. Now, the final step in this question is writing out the rate law. Now, remember, okay, rate laws are always written the same way. The word rate is equal to the rate constant. You don't need to solve for the rate constant. You don't have any information to do that. I just want to know what those exponents are going to be. Okay. Now, when given a mechanism, you can give me this information. If you notice, I didn't give you any trials, any data like that, but I did tell you which of these was the slow step. If I tell you the slow step, the coefficients for your reactants can become your exponents, but only if I tell you the slow step. So this is concentration of A2B2, and that's a coefficient of 1 in that step, so you don't have to write the 1 in, but I did there. Okay. Now, X is also over there. It's a catalyst. You don't technically have to write the catalyst in the rate law, so we're just going to go ahead and leave that out. So those are 4 sample problems of some things that you can see. Our kind of last big topic that we talked about, and I just want to leave you with and make sure that you review, is sticking with equilibrium is talking about Le Chatelier's principle. All right. So remember, this is when a stress is put on a reaction that's at equilibrium. The reaction is going to respond by trying to undo that stress. So let's just take something at equilibrium. We'll go, it's really easy. So I'm just going to make something up. 2A, and I'm going to say all of these are gases, plus B, that's a gas, is going to yield, we'll say 2C, and that's also a gas. All right. And I will tell you that this reaction has a delta H that is negative. If I tell you that, that means it's exothermic. Okay. So if it's exothermic, you can actually think of energy as a product. All right. So here is my reaction. It is at equilibrium. I've got those arrows going both ways. Great. I'm now going to put a stress on the system. The simplest way of thinking of this is whatever my stress is that I put on, the reaction is going to respond by trying to do the opposite of my stress. So if my stress is I'm going to increase the concentration of A, the response by the reaction to try and restore equilibrium is going to be the opposite of that. So what's the opposite of increasing the concentration of A? It's going to want to decrease the concentration of A. Now, how can that happen? Well, to take A away, I'm going to need the forward reaction to go. So it is going to, there's different ways of saying this. We could say it's going to shift right, or we could say the forward reaction is favored. There's just different ways of saying that. And again, why did this happen? Well, the stress was an increase in A. The response is going to be to take A away. How do I take A away? I have more forward reaction. So we can deal with concentration. I can deal with energy as well, and this will typically be in the form of temperature. So let's say that I increase, all right, the temperature on this system. So these are just different examples I'm giving you. That's my stress, is that I'm increasing the temperature. What is the response going to be? All right, the response is going to be the opposite of that. So my response is going to be to decrease the temperature. Okay, let me not use that arrow because I don't want to confuse. So we're going to say my stress is increasing. The response is to decrease temp. Well, how am I going to decrease temp? Well, temperature is a measure of energy. I want to decrease it, so I want to use it up. How am I going to use it up? I'm going to have that reverse reaction go. All right, so this is going to be a shift left, okay, to use up that energy. The final thing we talked about is talking about changes in pressure. And remember, an increase in pressure will move the reaction to the side with fewer moles of gas. So we'll move the reaction to the side with fewer moles of gas. And we will tell you, just like I did here, whether things are gases. And to count up moles, you're just counting up coefficients. So I have 2 and 1. So this has a total of 3 moles. This is just 2, so that is a total of 2. If I increase the pressure on the system, it's going to shift right. We have a lot of examples with the Chatelier. Please make sure you review those. Those are great places for us to get multiple choice questions. All right. As always, good luck on the test tomorrow. Please make sure you review all of your notes and all of the practice that we've done. All right. Take care.